There are two main concepts in modern operating systems to enable parallel execution. First is the most familiar if you have used any operating system newer than Windows 95, and that is the concept of task or application or process. The first operating systems were not able to provide simultaneous execution of multiple tasks, as the process of switching between them was quite expensive in terms of processing time. So in those cases, you would work in the prompt task of your operating system, and then you will run some command and it will load and launch the application, let you work with it, and when you are done, return to the prompt. This was a simple and elegant solution, but running one task at a time was not sufficient for many business use cases. So we have developed a system of abstraction layers that allows each application to execute in what is called virtual address space, as if it was the only program running on a computer. But at the same time, it is not the only one, and operating system and hardware provides isolation between tasks on the memory access level through memory mapping. In simple terms, the memory addresses that every program sees are converted on every call into real addresses through special lookup tables that are maintained by operating system. The lookup is usually hardware accelerated and almost as fast as direct memory access without this memory mapping. This approach allows operating system to suspend execution of any app at almost any given moment of time and share execution time on a single or multiple processor cores between multiple tasks. Usually, operating system will give each task a time slice of 1 to 10 milliseconds to do its things, and then it will force suspension and let another task run. Sometimes you might encounter failures in this mechanism when some task malfunctions and for some reason cannot be suspended or terminated by operating system, and does not finish its own tasks. In such cases, your computer freezes because no other task can run, and your input cannot be processed by neither operating system nor other tasks. So we can use this mechanism and simply create multiple single-core programs that will each have its own set of arguments and wait for them all to execute as independent processes and return the results. The largest drawback of this method is that tasks have this virtual memory isolation and cannot easily share data between each other. It is possible through different mechanisms that operating systems provide, but those are operating system specific and are not always very reliable. Another mechanism is more useful when you need to have a lot of execution happening on the same dataset. For example, when you invert some large matrix. In such cases, you can have parts of your program executed in parallel, but you need to work on the same set of values. For such cases, operating systems provide a concept of a thread. A thread is a part of a process. Each process will always have at least one main thread, but this can have more than one. Through special operating system calls, a process can create additional threads that will behave as independently running programs that share virtual address space. This is the hardest but the most efficient way to implement parallel execution on the same machine. The hard part comes from the fact that operating systems do not guarantee any specific order of execution for threads or their priorities, and otherwise treat threads in exactly the same way as tasks, so the threads can be individually suspended, resumed, moved between processor cores, and the program mostly has no control over this process. And this creates issues when the same data is to be written or read by multiple threads, and reading and writing should happen in specific order. For example, let's say we have a problem where multiple threads should get some external data, for example amount of cars on a specific road, and they should add this value to a single global variable. Now, if we imagine that we have just two threads A and B, it is possible that due to operating system interactions with threads, the following order of operations will happen. First, thread A will get its result and read the current total value. Then, it will be suspended. Then thread B will get its result and current total value, and it will calculate its version of the outcome and write the total back. Finally, thread A will be resumed, and it will also write its version of the total value back. And now we have a problem. Because thread A read the value first and wrote it last, the modifications that were performed by thread B were completely discarded. This is an example of what is called a race condition. The worst part about this issue is that it is not deterministic in nature. In theory, your code might be written in such a way that it will work just fine 99.9% of the time, and you will be unable to detect this issue in testing. But once your code is shipped to your customer, it will be executed for some continuous time, and even though the probability is rather small per each execution, when the time is involved, the problem will appear eventually, and it will cause a lot of problems. The topic of mitigation of these issues is quite broad and deserves its own course, so we're not going to handle these issues and resort to use of simpler and more reliable approaches. For example, from now on, when I am presenting threads in Python, you should keep in mind the following. In Python, threads are not truly asynchronous by default. Even if you create multiple threads, only one of them will be active at a time, and most of Python operations, such as accessing values in the list, are considered atomic. That means that they cannot be interrupted by operating system to switch your task to another thread. The key element that protects these critical operations is called Global Interpreter Lock, or GIL. There are ways to disable GIL protection in the Python code, but that will only actually work if you write code using Python, so for now, just forget that this option even exists. And now let's have a look how we can convert our existing serial code into code that uses threads and parallel running processes. In order to implement simple multi-threaded application in Python, we will need to use threading module. And from that threading module, we are going to import thread. That is a template class that can be used to implement your own classes that will run your code as a separate thread from the main application thread. How it looks like. Let's implement this myThread class, and let's inherit it from the base thread class here. And we will override two functions. First of all, we will override constructor, and we will compress all arguments, both positional and keywords that are passed to this construct, into args list and kwargs dictionary. And then we will forward keyword arguments to the parent constructor, because thread only expects keyword arguments actually. And the rest can be saved in this myArgs variable, and we will use this positional argument list to implement actual arguments of our code in the future. The second part is this run function. In the default thread class, this is a default runner of your problem, and if you override it in this way, then the thread will start running the code that is written in this function whenever you launch its execution. And in our case, we want to do just two prints. You will first print the I am a new thread string, and then we will print out the myArguments list to see that it has been saved correctly and passed correctly to the thread. So let's create this class, and let's try instantiating one. If we run this code and copy the thread variable and run it, you can see that we have created myThread thread4 initial state object, and this is the default representation of the class thread, and this is the identity of the thread, because every thread will have its unique number. And then this is the state of the thread. So in this case, it tells us that it is initial state and it hasn't been started yet. To start the thread after you have created it, you need to call start function. If you run it, you will immediately see the result of execution of the thread in this case, because we have no delays or any long-term queries and so on. And if we rerun this thread code, we can see the status of our thread has changed into stopped. Once the thread is stopped, we can call another method that is called join, and this will cause the child thread to be properly reconciled with the main application and destroyed from execution. So after you have called thread join, you will no longer be able to run the thread again. This was a fast thread and it doesn't really indicate what was going on here. So let's add another one. Let's add a slow thread class. This one is exactly the same, but it has a different name and it has a delay of 20 seconds between running the first print line, where it says I'm a new slow thread, and my slow args and passing the arguments away. So to test this, we are going to create two threads. One will be our default myThread, and the other one will be our slow thread. And we will save them into two different variables, and then we will start them sequentially, starting from the slow thread in this case, but in reality it doesn't really matter in which order we start them. And then we will ask our system to join slow thread without checking whether it has stopped or not, and after that we will join the main thread. What happens when you are joining a thread that has not been stopped? You actually will suspend execution of the main application until your thread has been properly joined. Let's run this code. As you can see, we immediately have started execution of both threads, and both have printed their welcome message, but only the fast thread has printed out 1, 2, 3, 4, 5, and we have not came out of execution here, because we are now pending on slow thread to complete its wait period of 20 seconds and print out my slow args and complete the execution. And now you can see that it has been done, and the slow thread has printed out the list of arguments that has been passed to it properly, and finally we have both threads rejoined. So this is a very simple way how to start threads in Python. Threads are in principle more or less independent, so you don't really need to think about their interactions, except for the cases where they are writing and reading this, except for the cases when they are accessing the same variables for write or to read. And in such cases you want to keep your operations limited to only atomic operations. So for example, adding things to the shared list is considered atomic. Modifying single element in the list will also be considered atomic. But if you will try to go through different elements of the list in different order and modify them in some way, then you will probably get a race condition, especially if you are going to pause your execution in between. Another interesting thing about threads in Python is that your threads will actually not be interrupted by operating system until you manually call time sleep or other delay function. Let's try to apply this threaded calculation to our trains problem. So let's copy paste our code here, and let's use the same import, the same arguments. We will probably skip this part because we're no longer interested in testing this simple case. And if we run this, we can check that everything still works, and it does. Now, in order to implement thread solver, we will need to create our solver thread class. So we will first start with our template that we have started, and we will put it after preparation of arguments, because this is a code that relates to the execution of solution of our problem, so it should be declared here. And in fact, this solver class in the run, it will contain, maybe slightly modified, but our run solver version. And we will take this one first and just write it here, and we will somehow need to define this argument set, and we will no longer need this run solver because we will switch execution of actual solution into the threaded mode. Okay, let's have a look what we are missing here now. First of all, of course, we need to somehow get argument set, and we are already saving my args list. So in principle, we just need to take this my args list and that bucket here, or basically rename it in this case into argument set so that it can be passed directly. Then our system will actually run this code and it will try to return the values. But the problem is that thread doesn't really return anything, and threads in Python do not have return values associated with them. So we will need to figure out a different way to do it. To handle this situation, we are going to pass a list, and we are going to name it result list. We will save this variable into self of this class so that we can re-access it later. And in our run function, instead of returning this, we will take the list and append it to the results. This way we can take an arbitrary list of results that we will create externally before starting any threads and pass it essentially as a pass by reference value. And because we are passing it by reference, all threads will reference the same list. And if they all call append to that list, the resulting list will contain all values computed by all the different threads. And one more thing that we need to do is rename this one. Let's rename it solver thread. Okay, we have some threads that can do some computation. In theory, this should be enough to run a single problem and get result for a single problem. How do we actually parallelize things? So first of all, here, we will need to create a new list that will contain our threads object. We will have to preserve them so that we can first start them and then join them in an organized manner. Second, here instead of run solver, which we no longer have, we are going to actually instantiate our solver thread. So we are going to do it like this. Here we're creating a thread object, and we're going to first start it, and then also save it into our thread list. And we're going to first start the thread, and then we're going to save it to our thread list. Okay, now finally what we need to do is actually to join all the threads that we have started after they have completed their execution. To do that, we are going to iterate over the threads list that we take from here, and we are going to take every thread in that list and just call join on them. This way we ensure that by the time we reach this line and by the time we start post-processing results, we actually have all the threads executed and all the threads have returned the results into this processed list. And it doesn't really matter in which order we are going to wait for them, so long as we are going to wait for each and every one of them. Okay, the next step that we're going to do is we're going to modify this run to also include argument set. To do that, we're just going to copy it and add another layer here. We will add an external list and comma and use argument set as the first argument and then the result of execution as the second. In this way, we are ensuring that our arguments are passed together into the results with the same results they relate to. Otherwise, with the threaded execution, you cannot guarantee in which order the results will be written into the list. And now in the processed results, we will contain a list of these pairs, where first element is our argument set, and the second is our result set. And this is exactly what we are going to expect after zipping these together. So in this case, we no longer need to zip it because we actually do this already with this line. So we can just replace zip call with just reference to the processed result list. And let's try to run this code. And as you can see, it has executed successfully. And we didn't have any problems whatsoever, and the system didn't even notice that we actually have created a lot of threads to run things in parallel. Now, as you remember, threads in Python are not really asynchronous, so that is not a perfectly illustrative solution, because the threads are still executed in one way or another sequentially. The order of execution is not determined, but they still will not be run at the same time trying to do the same thing. Let's have a look at a slightly more upgraded version, because right now we have this whole mess of adding results lists and managing the passing of arguments into our functions and doing a lot of unnecessary actions actually. In Python, there is so-called multiprocessing module, and multiprocessing module is actually intended for running multiprocessed application, meaning that you will run more than one actual processes that will do some kind of calculations in parallel together. But it has a small submodule that is used primarily for testing that is called dummy. And we are going to implement this. So we'll first import this multiprocessing.dummy, and from there we are going to input pool. Pool in terms of programming is basically a set of some resources. In our case, the pool is a set of threads. We are going to create a pool that will contain 12 threads. If you have noticed before, we have basically created one thread for each possible call argument, which is less than optimal because creating and destroying thread is still quite computationally heavy task. In this case, we're going to start just 12. This matches the amount of logical cores I have on my machine. In case of virtual machine, it will be still limited to 6 of them running at the same time, in the best possible case. And we are going to use this threaded pool to actually dispatch our processing. To do that, instead of solving this problem in this way, we are going to do a little bit of reversion back to the solver that we had before. So we're going to use this run solver function again, and we're no longer going to use threads at all. Instead, we're going to have a very simple call that looks like this. And this function takes thread pool object and assigns this task to that thread pool. Map is a function that performs computation on lists, and what map does is very similar to iteration by a list. So map for this case effectively will take processed result as a second argument and will take this formatted as a function as first argument. So in our case, this thread pool map effectively runs iteration as if it was a for loop for every element of this call arguments list. And for every element, it will pass the arguments into this run solver and take the values that result from execution and store them in the resulting list. So it converts this list of values into this list of values. And in the process, it uses this run solver to convert one element of this list into one element of this list. Here we will need to also revert back to our zip, because we're now using again the simple run solver, which does not create a list of lists. And because threadpool.map actually preserves the order of results, we can do this safely. So we know for sure that zero element of call arguments has been called and the result has been saved into processed results 0. And call arguments 1 has been passed into run solver and the result has been saved into processed results 1, and so on. And if we zip them together, we're going to get our pairs of arguments and the corresponding results. Let's try running this code. Okay, we have thread pool that is undefined. Okay, this code must go all the way down here, and we will need to undo all the changes we did in this cell by pressing Ctrl Z. Okay, let's try running this code. And as you can see, our thread pool has been created actually twice, and it has been actually correctly executed, and we have got the results that we expect. Now the only problem is that we have this pool and it is being created every time we run the cell, and because Python does not delete these pools immediately, we need to manually close this pool as well. You can do this by running threadpool.close, and this function is similar to calling join on every thread manually. It will just do this in the automated way. Okay, this is how we are going to use threads in the future. So this is the most convenient way to just take a list of formatted arguments here and then pass them directly to the solver function. So no need to define classes, no need to override any runners functions, and you can just get the results directly mapped from your arguments via the function. Now the last part is to actually implement the real multiprocessing. So we are going to step out of the dummy and start running things in real separate processes. The problem with this is that it doesn't really work well with Jupyter Notebook. So we are going to do this in Python script. So let's open our editor and let's create a new file here. So we will touch and create solvetrain.py and we will open it. Now we're going to copy paste contents of our notebook. So first of all, we are going to copy paste this part because it is necessary to actually initialize the initial conditions for our problem. Then we're going to import our functions to compute things the same way. And finally, we are going to copy paste the last created cell, the part 2 with threads, so that we can run them. Now we will have to do the following modifications. So first of all, we're going to get rid of dummy, and we're going to import pool directly from multiprocessing. It is exactly the same object with very similar API, but instead of threads, it creates actual processes. I'm going to rename this threaded pool with just pool, because we don't want to confuse people reading this code. And the operations are exactly the same. So we create pool, we map the arguments via the function into the results, and then we close the pool once we are done. Now the problem is that if we run this code right now, the multiprocessing module will try to import the run solver function from this module. And while doing that, it will actually go into more or less infinite loop trying to process this module before it will be able to import this function. In order to avoid that, we're going to move this run solver function first here, and we're going to move these imports as well because they are necessary for this run solver function. And the rest of the problem we are going to wrap into our if _name equals _main _clause. And this will let us have the module and the function exported from this module safely, but without executing any of the actual code during this process. And the problem is that now the editor wants to add tabs. So we are going to copy paste this back into Jupyter first. This is not the best editor for doing this, and we're going to add tabulation here, copy it back, and return into the edit. Okay, now we have properly indented code with spaces. Okay, let's try running this. And as you can see, it works. So at the first iteration, we have name set to main.py, and because it is set to main.py, it starts the thread, it will import the functions, and it will run the computations. To prove that we actually are creating multiple processes, I am going to use htop-util. That is a process manager for Linux, one of the many. And here you can see that we have 6 cores, and currently they are not loaded. And we are sorting our processes, the names of the processes are listed on the right, by CPU time. So if we have this on the right side, and our script running on the left side, and modify this problem a little bit so that we have more iterations. So we will increase the density of steps to 1, and we will change the minimal value to also 1, and save it. And let's run this code. In our computation, let's add an artificial delay. We can make an iteration for some variable. Let's name it I, and let's repeat our computations 1000 times every time before we return the results. So like this. And now we finally see the 100% loading of our course. And after some time, we actually get back the results. Let's delay this a little bit more. Okay, as you can see, the results are still visible here. Oh yeah, because it was not sorting by the CPU. Now you can see that we correctly run multiple instances of solve_train.py, and these are white lines, which means that they are independent actual processes. And that is how you make parallel processing of data in Python when you need to utilize large number of cores in the cheapest possible way. Because in this way, you actually avoid a lot of problems that are inherent in parallel computations. If you can decouple your problem in such a way, then it is what is called embarrassingly parallel code. To summarize, so in order to handle parallel execution in Python, you can use either threads or processes, and threads are not really parallel unless you do some specialized tricks. And the other option is running actual separate processes. In this case, each of the processes will have its own global interpreter lock, each will have its own set of variables, its own memory, and you will be able to actually execute things without being linked together, so long as you can decouple your problem in such a way that it just takes a set of arguments and returns some results, and does some reasonably heavy computation in between.